Hello and welcome to another Algebra 1 screencast. Today our lesson is all about solving systems of equations with graphing. This is the first of your techniques. You'll learn some other techniques like substitution and elimination and some lessons to follow. And for today, we're going to try and keep it simple with just looking at some of the basics of what a system is and how you would solve it using the graphs. I'd like to start with this warm-up activity. If you're watching at home, and you can pause the video here, work these 3 warm-up questions out, and then we'll rejoin together as a class to discuss them. So go ahead and pause the video, and we'll pick back up in a few moments. All right, assuming you've had some time to work on your warm-up questions, let's look at this first one. We are asked to consider the equation and then whether or not 6, 0 is a solution. So you'll remember that to be a solution to an equation just means that if I plug in 6 for x in this case and y for 0 in this case, do I get a true statement? Well, let's see. If I plug in y for 0, or rather 0 for y, and 2/3 times x is going to become 2/3 times 6, since I'm plugging in 6 for x, we want to see, does this equal a true statement? Well, 6 over 3 is going to wind up being 2 times 2, which is 4 minus 4. We got 0 over on the right, 0 on the left. Both of those obviously are equal, so we would say, yes, this is a solution to the equation. And then similarly for part B, we would plug in -2 for y. We'd plug in, instead of 6, we're going to plug in -3 for x and see if this is a true statement. 3 cancels out there. We got 2 times -1 is -2. So does -2 minus 4 equal -2? We would say no, it does not. It equals -6. So this point is not a solution to the equation. We're also asked in this warm-up to consider the idea of slope and y-intercept. This equation in number 2 is given to us in standard form, so let's get it in y equals form. We'll get it in y equals form. I would suggest adding y and subtracting 12 from both sides such that we get y equals 3x minus 12. You might have taken some other steps, but hopefully you got it in y equals form, because now we can identify 3 is our slope and -12 is our y-intercept. So 3 is our slope, and -12, don't forget to put the negative with the 12, that's going to be our y-intercept. And then when it says find the x-intercept and the y-intercept of this question, that's just a matter, again, of plugging in, hey, I want to let x be 0 and see what y is. That'll be my y-intercept. And then I want to plug in y is 0 and see what I get out. That'll be my x-intercept. So we can do this in just a couple of moments. We'll take out the 0 term, divide by -3, we get y equals -4. So that's our y-intercept. And then when we, in orange, when we take out the 0 term, we divide by 2, we get x equals 6. That's going to be my x-intercept. So just some basic warm-ups talking about linear equations and their graphs. Let's get into the lesson. So when we talk about a system of equations, first of all, you need to understand that a system of equations is just where they're grouping more than one equation together. So like for this first example, we're considering 2 such equations. Now they're both in standard form. They both have an x and a y, so this is a system of linear equations. And if we graph them out, they will very likely look something like this, where you've got, one line going this way, and you've got another line going this way. And the notion of the solution to a system of equations is we're looking for the ordered pair or ordered pairs. For other systems, they might have more than one point. You're looking for the point of intersection. We're looking for that point right there. So when you're asked, hey, is this a solution? What you're being asked is, hey, is this a point that's on both lines? Is it on the blue line? Is it on the green line? And if you would say yes to both of those questions, then you would say, yes, it is a solution. So just like we did in the warm-ups, what we could do is we could easily plug in the x value and the y value to see if it gets a true statement in both equations. Again, because we want to make sure that it makes a true statement in all of the equations. All right, so let's try and do that rather rapidly. We'll plug in -2 for x in the first equation. We'll plug in -1 for y in the first equation, and we'll see, does that make a true statement? Well, minus negative is going to become plus positive, so we got -2 plus 1. That does check out. So this is a true statement on the first equation. Let's see if it's a true statement on the second equation. 2 times -2 minus, and then again we're plugging in -1, and we want to say, hey, does this equal -5? Let's see, -4, again plus positive there for that one, and this does not equal -5. So we would have to say false, and therefore a no to this one, again, because it has to make a true statement in both equations. When we try the second one here, this second example, we'll plug in -4 for x, we'll plug in -3 for y, and we'll check, does this in fact equal? Let's see, -4 plus positive, and that's going to end up, yes it does, equal -1. So we get a true statement on the first equation. And then if we plug in again -4 for x into that second equation, so we got 2x minus y, and -3 goes in for y, we want to see, hey, does this equal -5? -8 plus 3, it does equal -5. So we get a true statement in the second equation as well, and therefore we would say, yes, this is the solution. In other words, graphically speaking, this is the point that was on both lines. So example 1, just checking to see if something is the solution to a system. Next, I'm going to scroll down and we're going to talk about how there are 3 possible scenarios here for your system of linear equations. The first one, as we mentioned a moment ago, is where there's one and only one point of intersection. Right? So there's one solution for this type of system. It's called a consistent or an independent system. So there's one solution, one point of intersection. Okay? An inconsistent system would have no solutions. That's the symbol for no solutions. And then I recognize that my highlights are off down here a little bit. When we look at, there's one solution, there's no solution. When we look at this third situation, it's a little bit interesting. It looks like there's just one line drawn out, but that's because both lines are actually drawn one right on top of the other. So we would say there's infinitely many solutions to this system of equations, and you would consider that one to be what's called a dependent system, if you will. The middle one, where no solution is, it's called an inconsistent system. So the majority of the problems that we work, fellas, will be in this scenario right over here, where you've got a consistent system, you can find the answers, there's one and only one solution. Every now and then you'll come across a no solutions or an infinitely many solutions, but in this case, a vast majority of our problems are going to be very much solvable. Now, if you're one that likes a good step-by-step approach, this is the approach for you then. How to solve a system by graphing it out. I'll encourage you to pause the video now if you're watching at home, jot these steps down, and then we can move on with our next example. So go ahead and pause that video now, jot these steps down, and then we'll use these steps in the next example. All right, so hopefully you've had a chance to copy these down. We'll be using them in this example 3 right here, which says solve the following system by graphing. Now, the first thing I would like to do is I would like to get each of these in y equals form. I'm a big fan of slope-intercept form. It makes things easy to graph. So I'm going to let y stay on the left side. We're going to subtract 2x from both sides, and then that 7 is going to be there as my y-intercept. That's my first line. And then the second one, I'll do the same thing. I'll solve for y. So in this case, I'm going to subtract x divided by -2. So I get y equals. Now, when you subtract x from both sides, that's -1x. Divide that by -2, and it becomes a positive 1 over 2x. And then 6 over -2 becomes -3. And those are going to be the two y-intercept or slope-intercept forms of these equations. Let's see if we can graph them out. So the first one, we have a y-intercept of 7. So 1, 2, 3, 4, 5, 6, 7. That's going to be where I put my starting point. Remember, with the y-intercept or slope-intercept form, you're going to start at the y-intercept, and then you're going to use the slope as your sort of directions. So that slope of -2 over 1 is going to tell me to drop down 1, 2, and then run over 2. So I'm going to go down 1, 2. I'm going to run over 1, go down 1, 2, run over 1. It's got a negative slope. It's going down and to the right. You'll remember that from our discussion. And then try and draw a nice straight line through those 3 points. And again, this is a very approximate approach to solving these systems. Down here, I'm going to start at -3. Again, for my second line, I'm going to start at the y-intercept. So 1, 2, 3. And that's going to be my first point. This will be my starting point. And then I'm going to go up 1 and over 2. So again, this is where I go using my slope. So we're going to go up 1 and over 2. So I go up 1 and then over 2. Go up 1 and then over 2. And it looks like I might have found my solution. We'll see in just a moment. We're going to check that solution out, but we got to connect the dots right there and right there. Now use your eyes and sort of try to determine, where is this point? What are its coordinates? Well, it looks to me like we've got 1, 2, 3, 4 as an x coordinate, and it looks like -1 as a y coordinate. So that looks like the solution to this system, the point of intersection. Now the way that we check that, again, is we plug in the coordinates to make sure we get a true statement in both the first and the second equation. Let's do that real quickly, just like we practiced a moment ago. 2 times x is going to become 2 times 4, and then plus y, so we'll plus -1. Notice a couple things. First of all, I'm using parentheses when I plug those things in, when I plug those coordinates in. And 8 minus 1 certainly does equal 7. So that's a true statement on the first equation. And then the second thing I want you to notice is that I'm using the original equations. I'm not using the slope-intercept forms. I'm not using these guys over here, because what if I made a mistake? What if I messed up solving for y and I plugged those coordinates back into those messed up equations? Then it's sort of like a self-fulfilling prophecy here. And I would get a true statement, even though that's sort of like a false positive there. All right, so this checks out. Looks like a good solution to this system. So I hope this has been a helpful video for you on how to solve systems of linear equations by graphing. Once in a while, as I mentioned, you'll come across, if I could go back to this previous screen, you'll come across a system where the lines don't intersect. So if you graph them out, fellas, and you notice, ooh, these lines are parallel, they have the same slope, but different y-intercepts, there will be no solution to that system. And then if you have same slope and the same y-intercept, right, then that's going to be a case where there's infinitely many solutions, because that's actually just the same line in disguise. I'll go ahead and show you. We won't work them out, but I'll go ahead and show you a couple of special cases. Like, for example, right here, if you want to try this example out on your own, this is one of our 2 special cases where the slopes are the same, but the y-intercepts are different. So I'll give you a hint. That's going to be where we have parallel lines, right? See if you can find a point of intersection there. And then this last example is where, again, another special case where these 2 lines, they're really the same line in disguise. They're actually just in different sort of formats, if you will. So that would be that weird graph where it's one line and then right on top of it is another line. See if you can find how many points of intersection there are in that example. But like I said, the vast majority of our problems will be just like example 3, where you can find the one solution. So as I mentioned, I hope this was a helpful video to you. This is how you solve systems by graphing.